Hello, everyone. Thank you for coming, and welcome to this session titled Improving Accuracy of GenAI Apps with Azure Database for PostgreSQL. I am Maxim Lukyanov, a product manager in GenAI team in Azure Postgres Service. And together with me on this stage, we have one of our great Azure Postgres customers from Europe. Jay Orun, would you like to introduce yourself?
Hello, everyone. My name is Jay Young. I'm a chapter lead in the RISLab Model Services. We provide platform and software solutions for over 1,200 data scientists and AI developers in UBS. I'm here with my colleague, Orhan. Would you like to introduce yourself?
Yeah, I'm Orhan Özbek. I'm a software engineer at RISLab Model Services team.
Yeah. Okay, thank you.
Awesome. So let's dive into it. So today we have 3 parts on the presentation. We'll start from the discussion of the improvements in the vector search, specifically our new DiskNN algorithm. Then in second part, we'll talk about improving accuracy of GenAI apps using advanced RAG techniques. Specifically, we'll cover semantic ranker and GraphRAG. And in the last part, my co-presenters will talk about the GenAI platform they have created at UBS, powered by Azure Postgres. And also they will cover another advanced RAG technique called hierarchical tree search. In terms of questions, given that we have very harshly allotted time, let's take questions probably at the end where we'll have Q&A. And then, so that's a procedural note. So let's start. So first, let's take a look at the basic retrieval augmented generation architecture. Many of you are probably familiar with it already. There are many elements in this architecture that determine the quality of your GenAI application, starting from chunking, to vector search, to generation of the responses using LLM, and last but not least, the evaluation framework. You need the evaluation framework to systematically track quality of your GenAI app, and more importantly, to be able to pinpoint to the element in the architecture that is responsible for the quality of the responses and may need to be improved. In our observations, we actually found that in majority of the cases, in one study, we saw as many as 80% of the inaccurate responses were attributed to the information retrieval pipeline. So that's some element of the GenAI app that is most having the most impact on today's GenAI quality, GenAI app quality. So in this talk, we will focus on information retrieval, and specifically, we will focus on 2 problems. The first problem is a problem of scale. Vector indexes are incredibly memory hungry, and trying to host medium to large-sized workload can become very expensive very quickly. And the second problem is a problem of accuracy. We hear from many of our customers who went from the initial POC stage to a production deployment that the solution is almost there, but the GenAI app still needs to improve its accuracy of the responses. The quality is not there yet. They don't want GenAI app to do more, they just needed to do a more accurate job of it. But once the number of vectors in the vector store, because we're talking about information retrieval, increases, or if the documents in your vector store are too similar to each other, the heart of the RAG application, the vector search, starts to fail and produce incorrect results. So that's the 2 problems. Let's start with the first one, the problem of scale. So first, let's take a look at today's industry. There are 2 widely adopted and popular algorithms in vector search that are being used almost everywhere. The first is IVF-flat, and the second is HNSW. IVF-flat algorithm is a clustering-based algorithm, and it has difficulty accepting incremental changes. And HNSW is a graph-based algorithm, and due to its structure, it is friendly to incremental changes. For that reason, it is more popular, although it actually requires a little bit more memory to maintain its representation in memory. So let's take a look at those 2 algorithms. One property, very important property that applies to both of them is that they lack information locality. So whenever you perform vector search, the way the process works, it basically resembles a random jumps across the memory, right? From one point in the graph to another. So that results basically in a vector index requiring almost all of its data to be resident in memory. Otherwise, the performance drops dramatically. So this makes both of those algorithms a memory-only algorithms where the full data set needs to be in memory. So this can get expensive very quickly. For example, in this chart, you can see how many gigabytes of memory in your VM, and we are talking about Azure Postgres VMs specifically here, you need to host a particular workload. So if you're talking about 2 million vectors, you need 32 gigabyte VM. And if you're talking about 8 million, we're already talking about 128 gigabyte VM just for vector store. And that will cost you like $4,000 a month. That's expensive. So that's why we partnered with, actually, Microsoft Research partnered with us. They invented the new algorithm, DiskNN, which you heard about from Satya during the keynote. And today we are excited to bring this DiskNN innovation to Postgres. So it's available across other databases as well. But now we have that in preview on Postgres too. So the way DiskNN resolves this memory issue is by using a powerful technique called product quantization. So it allows it to compress these very large vectors that we are dealing with today into a much smaller number of dimensions, resulting in up to a 30x reduction in memory requirements. And that allows us to achieve a much more efficient and cost-effective way of serving indexes. The algorithm is also designed for both delivering this high efficiency as well as high accuracy. So it does a search in two stages. In first stage, it uses compressed vectors, which have lower accuracy to retrieve the initial candidate list. But then in the second stage, it uses full vectors to re-rank these results and bring back the accuracy up to the kind of a normal vector search quality level. So that allows us to combine basically memory efficiency with high cost efficiency as well. So if you look at an example, so here we're dealing with 4 million vectors. Without product quantization, if you put these 4 million vectors on the VM, and we are here using 32 gigabyte VM, then the latency of the request will spike to 500 milliseconds. That's, you will see the bigger chart, right? But if you use product quantization, then all of the vectors will fit in the memory because they're compressed. And latency drops dramatically to 12 milliseconds. So that's a 40x improvement in speed on this particular VM, right? But you might ask, hey, why don't I increase the size of the VM so I can store all of my full vectors, right, in memory? So that's a cost argument, right? So if you want to achieve similar interactive latency in the vector search, we can basically provision the same 4 million vectors on 2 different VMs, right, that deliver the same speed. But with full vectors, you will have to provision 64 gigabyte one, right? And with product quantization, you'll be able to reduce it down to 16 gigabyte. So that's 4x improvement in cost. And the best part, that equation applies to all scale points, right? Starting from small, in this case, 1 million vectors, to 8 million vectors. You will see the improvement across all of the VM sizes. And again, we are talking specifically here about Azure Postgres VMs, right? Which is very concrete and real scenarios. So if you go up to 8 million vectors, then you'll be paying roughly 2,000 more, right, if you're not using product quantization. So that's great. DiskNN gives us a very cost-effective and highly accurate vector search, right? But how do we go beyond that? So how do we ensure that the RAG application as a whole delivers high-quality results? So let's talk about advanced RAG techniques. So first, the question is like, hey, is it even possible, right, to improve the quality of RAG applications? Well, the good answer is it is. And there are lots of actually ways how you can go about it. if you look at basic RAG architecture, then by improving chunking strategies, using bigger embeddings, applying query rewriting, applying hybrid search and metadata filtering where applicable, you can dramatically boost accuracy of your application already. But if you want to do even better, then you can add additional components, and that's why we call it advanced RAG applications, to improve quality of the GenAI applications using these additional advanced techniques. So for example, hierarchical summarization is very effective, or you heard at Keynote, the agentic systems can use metadata techniques to improve accuracy as well. In this talk, we'll focus on semantic ranking and graph RAG, because we found in our applications they're quite effective, and specifically semantic ranking is broadly applicable. So let's talk about semantic ranking. So the way it works, the idea is improve vector search results by using kind of a more precise, more accurate semantic ranking model to re-rank the results. So let's say we can retrieve 100 vector search results, right? Then we'll take each item, and we'll take the text of the item, and we'll use semantic ranking model to compute relevance of that item to the actual query string, right? And then we'll use these relevance scores to find the real top 10 out of this 100, right? So if semantic ranking quality or accuracy is better than vector search, then we'll get improvement in the quality of the results. There are a few popular types of the semantic ranking models. The most popular one is a cross-encoder model, which is fairly fast and produces good results at the same time. So the cross-encoder model is built on kind of a BERT type of the large language model, and it's produced by fine-tuning that model for this relevance task. It takes query text and item text, concatenates them, and computes the relevance score. So that kind of joining of these two elements is why it's called cross-encoder model. So it is fairly large model still, and it requires GPU hardware, so that's kind of the downside. But it is fast, and it produces better results. So that's an upside. But the actual quality of the cross-encoder model depends on its size and on the data set that it was trained on. So which cross-encoder model should we use? So we did a comparison of semantic ranking models in the open source domain, and this is the results that you can see. In this table, we use NDCG quality metric, which represents quality of the vector search on a scale from 0 to 100, where 100 is basically a perfect, absolutely correct result. From the table, you can see that the BGE Reranker V2 M3 model produces the best results, achieving 66% of the quality rating for these 9 data sets that we used in the testing. And it achieves 12, or it produces 12 percentage points of improvement over the plain vector search, and we use HNSW here. So that's a significant improvement on the scale from 0 to 100. It will actually deliver tangible improvements that end users will notice in your GenAI app. So that's a great semantic ranking model, and it's worth doing it. So I'm excited to announce that today we are making end-to-end solution accelerator available to you, or how you can extend your Azure Postgres deployments with the semantic ranker capabilities. So this solution accelerator provides you automated deployment script that deploys this BGE Reranker model, or it's easy to switch to any other, into Azure ML as an endpoint. And then it provides a SQL integration script where you can integrate SQL directly in your Postgres and do semantic ranking directly from PostgreSQL query. So here is a blog post with much more details about semantic ranking and solution accelerator, and of course, the repo where the source code is available to you. Great. So let's go to the next technique called GraphRag. So GraphRag is another technique invented by Microsoft Research. The idea is to basically index your unstructured data, right? Extract graph relationships from it, and use these additional relationships in your data to improve accuracy of the responses. So there are 3 key steps. It's a very interesting technique, so I certainly recommend going to this website and the papers that describe the technique to learn about it in more details. But at a high level, there are 3 key steps to the technique. First, GraphRag extracts a graph from the unstructured data by asking LLM actually to detect entities and relationships between entities in your data. Then it uses summarization technique to summarize the relationships and entities discovered in the graph to build summaries of them. So this is a key step of the technique because it allows to improve accuracy of the vector search, because it gives vector search alternative representations of your data. And that improves accuracy, or specifically recall of the vector search. So finally, once a graph is built, the technique generates graph queries to take advantage of these relationships to improve accuracy. So we'll take a look at how it works in the demo later. So GraphRag stores data in a graph representation, right? It's a key data structure that it uses. So it needs to store it somewhere. So I'm excited to announce that we are making graph storage natively available in Azure Postgres through an extension called Apache Edge, sorry. Thank you. So one additional reason why it's exciting is because it illustrates the power of Postgres ecosystem, which I'm always fascinated about. There are so many open source projects and extensions for Postgres that allow you to do basically anything with Postgres that you can imagine. So one of those things is turning your Postgres database into a graph database. So you can install this extension that is now available in our service, basically run a popular and widely accepted standard of graph queries called Cypher on your Postgres database. You can also mix your graph queries and your traditional relational queries together, and you can use Postgres indexes on your graphs to improve performance and scalability of your graph database. That's a pretty nice combination and exciting extension. So now we are taking these 2 techniques, the GraphRag and Apache Edge, and going to another announcement. Again, today, we are happy to announce another solution accelerator that presents you with an example or end-to-end solution of how we can use GraphRag technique, combine it with Apache Edge graph extension, and build end-to-end GraphRag GenAI application on top of Postgres, using Postgres as a unified data platform that keeps everything together. So this solution accelerator is an example of an actual Copilot application in legal domain. It uses public data set of a US case law, 500,000 of them, to basically build a recommendation app that allows you to research legal questions. As you can see from the architecture, it uses GraphRag to summarize the graph of the legal entities, store it in Postgres, and then uses it during chat session to augment the accuracy of the responses. Again, in the demo later, we'll see how it happens. If you want to learn more, there is a blog post that we published today and full source code with all of the details of the demo that you see available for you in the repo so you can reproduce it and build your own systems. So before we jump into a demo, a quick comment here is that the graph extraction, entity summarization, and the third step, graph query generation that I mentioned is part of the GraphRag were customized for this particular demo. So we discovered that using natural graph relationships in the data actually helps improve accuracy of the GenAI applications. So for that reason, we actually used the graph of the citations between legal cases as a kind of a natural graph of the data that we use in our GraphRag. So instead of extracting graph from the actual text, we use a fixed graph that is already present in the data. And then we also customize the query to take advantage of this citation graph that we have in the legal cases. So with that customization, we are ready to jump into a demo. So let me switch to a demo. So this is our legal research copilot application. It allows you to research various legal domains, right? So our example question is water leaking into the apartment, right, from the floorboard? And what is legal precedence in the Washington about that? So if you ask this question, and hopefully the demo still works. Yeah, it's great, works. Oh, and this is semantic ranker, sorry. Let's scratch that, you didn't see it. So let's switch to vector search first. So if you use vector search, right, the response that we get is somewhat good, but is an example actually of a misleading answer. So the first legal principle it detects is correct, but the second one, it talks about different wrong things, is incorrect. It actually struggles to find even relevant references sorry, into the underlying data. So what happens, right? So we can use this graph representation, graph view, to debug why this response is wrong. So this is a graph representation of our legal data that was retrieved by the vector search. So it represents a graph, but the vector search is unaware of graph relationships, right? It only knows about the text. So first, let's take a pause here to understand what we're looking at. So this node is the legal cases. The size of the node is proportionate to the number of citations from other legal cases that this legal case has, right? So the bigger the case is, the more prominent it is. The arrows is the citations, right? The golden color is very important because this represents a golden data set, the correct answers according to human judgment for this particular question, right? So we want all of the golden sets to be returned by vector, golden nodes to be returned by vector search. And the green circles here represent the actual returned answers, right, by the vector search. As you can see, vector search didn't do a very good job. It only covered 4 out of 10 legal cases here, so its recall rate is 40%, very low. So that explains why the response from the LLM was incorrect, because it was based on the wrong data. So how do we improve that? We can switch into a semantic ranker mode, right? So we'll apply semantic ranker and improve results. So now we get recall rate up to 60%, and you can see more of the golden circles are found. And finally, let's apply GraphRag technique and start taking into account this relationships, right, and prominence of the legal cases. So if you do that, then finally we are able to detect correctly these prominent legal cases, right, and improve recall rate to 70%. So if you go back to our app and ask this question again, but in the GraphRag mode, we can see that the response is now of high quality, right? It detects 2 legal principles correctly. And more importantly, in explaining these legal principles, it uses prominent legal cases, right? This is exactly how I would like to learn about a new problem in the legal domain. I would like to learn about it using some landmark legal cases that happened in this space. So that's a great example of how the technique works. And to give you a little bit of a look at the underlying graph queries, or queries that we used for this application, here is an example of the vector search that this application generates. And maybe, yeah, OK. So while it's connecting, we can explain the query. So here you can see various elements of the infrastructure, right? So we use Azure AI extension to automatically generate embedding for this question, right? And second, we use vector search here. This is a cosine similarity operator in Postgres to perform vector search. So that makes it relatively simple SQL query to do vector search in Postgres. So let's see, yeah, it's connected. So let's stop. No, Jadmin doesn't like that. We need to reconnect. Do we have time for this? Okay, we have 1 more minute. Okay. So let's do it again. Yay, it works. So quickly, semantic ranker example. So using solution accelerator that we provided, semantic ranking also looks very simple in Postgres now. So the solution accelerator provides you with this semantic ranking, a UDF, that basically makes a call to this model in AML and performs re-ranking of the results from the previous query from the vector search, right? So now you can see the results here, and you can see it's actually pretty interactive, right? And finally, the graph query. Let's run it. And while it's running, we'll talk about it. So graph query works on top of semantic ranker query, and it performs this Cypher query. So this is a key part. This Cypher query basically describes that we are counting number of relationships between nodes, right? And we are counting incoming relationships to the nodes. And which nodes we are counting? So here is a very nice property. We are doing a join with a relational query. So we can extend relational query with a graph query and join them together. It's very powerful. Actually not available, I think, in any other database system. Cool, so that's, and this is RRF, which fuses two ranking generated by semantic ranker and by the graph, right? It allows us to combine the information signal about prominence of the legal cases and semantic similarity. So with that, and with our demo successfully concluded, so what is happening here? We can switch to the next part of our presentation to my co-presenters from UBS.
Thanks, Maxime. All right, okay. So I will talk a little bit about the success stories of UBS leveraging Postgres, and later my colleagues will start talking about some advanced agentic retrieval techniques. First of all, on UBS. UBS is the leading universal bank in Switzerland. We are among the top 3 wealth managers in the world. With acquisition of Credit Suisse, UBS managed $5.7 trillion of assets, and actually we also operate in 50 markets. So the team I'm responsible of is UBS Risk Lab. It is actually the firm's largest data science, machine learning, and generative AI development platforms. So we serve over 1,200 data scientists in the back office functions, such as risk, compliances, and also the finance, and also front office teams in investment banking, and also wealth management. On GenAI, Risk Lab developed in-house ACE platform, stands for AI Common Ecosystems, using Azure services. It actually provides the data scientists actually with simplified the platform services and also UBS GenAI SDK on large language models, RAG, and agents. So what are the requirements of UBS on RAG? So the business use cases is we need to have a RAG as a service to build custom AI solutions. So Risk Lab has really 1,500 users. You can see here many of them, they want to do RAG in 2024. So building a dedicated vector store for every single use cases is just not scalable, right? So they want self-service functionalities able to create the tenanted vector store actually in less than a minute. And also the access controls to protect data, confidential data is very important. We're a highly regulated bank, so we need to have Azure, the AAD integrate securities for both the use case vector store tenant owners, the admins, the reader, and also the writers. Many of our data scientists, they like to perform advanced RAG techniques, as Maxime has really mentioned over there. So that actually then we will need to have a dynamic document metadata definition. That is very important. The lab work is really very experimental in nature. We would allow fast iterations. People come up with their own schemas. And of course, agentic friendly, in addition to the advanced retrieval techniques. Orhan will also talk later about advanced agentic retrieval techniques. Technical requirement, low depth of maintenance, and also scalable. Actually, we literally have hundreds or even thousands of vector stores. So here is our solution. Our product within ACE is called Vega. It's a very catchy name. It stands for Vector Embedding Governance Applications. It is a multi-tenanted vector store built on top of the Azure Postgre PG Vector. As you can see here, different vector store use cases actually will be going through an injection pipeline, which we'll talk later, into surrogated the vector tenants. Each tenant will have a set of roles, tenant admins, writers, and the readers actually being set up using the AAD authentications. In the pipeline, UBS RISLab, we pre-built UBS custom document loaders in accessing smart PDF readings, reading from the GitLab repositories, right? The document loadings for the SharePoints, or even Stack Overflow, right? Which really pre-built those things so our data scientists can concentrate on business logics. We treat securities very closely to our heart. We partner up with the industry-leading LLM SecOps vendors to protect the threat in the prompt injection attacks and also PII CID leakages. So we do scan all the content to ensure they are secure. Of course, the vector injection pipelines, we support Llama Index and also LangChains. Then on the retrieval part, and actually this is Orkan will talk a bit more later on, that is actually then we support many different agentic, the retrieval logics actually from the LangGraph and also the Llama indexes as well. Of course, the whole stack is really built on the Azure Postgre and actually it scales. So here's a quick demo on how easy to create a virtual vector store tenant if you're a data scientist. Of course, you need to log in using the Azure AD authentications. Once you're logged in, you are only able to see the list of the vector store tenants which you're a member of. To create a new tenant, just click on the collect button, enter a name, and actually stating the purpose, whether it's for your personal use or whether it's for use cases. Then you can using either like an email list or the main group for authenticating the admins, the writers, and actually the users. Of course, we have additional functions also to do your self-affirmations actually for the model validation teams, but actually then you just click on the create button. Then a brand new vector store is created in the pure self-service manner in less than 10 seconds. So our solutions are all API-centric. Not only you can create vector stores, actually through the GUIs, you can also do it programmatically. We support both the LangChain APIs and also Llama Index APIs. Then we build data scientist-friendly hybrid search APIs, so to simplify the development lifecycle. Everything can be used in a VS Code environment to fully manage the lifecycle of your vector stores. You can create, you can update, you delete, and actually perform additional advanced retrieval techniques. One of the really amazing use cases is actually we integrate Vega into our RAG benchmarking pipelines. So in UBS, actually, we test the qualities of the RAG pipelines actually using machine learning experimentation techniques. The concept is really very simple, right? To set up your best performing RAGs, actually you are going to try out the different configurations, such as different chunking logic, different chunking sizes, the chunking overlays, different agentic configurations. This can be translated as a hyperparameters in your machine learning experimentations. So in this example here, let me start. So this is really over kind of MLflow experimentations. Over here, I have RAG experimentations. Over here, I have 48 experimentation runs. Each pipelines, we connect with the Vega APIs, then we create a dedicated the vector store only for that one. So in that case, you have the full lineage about actually for every your best performing ones or your worst performing ones, actually you have the full lineage in the vector stores. So when going back in, actually the Nosy Dog 582 is actually the chunking runs. Over here, you can see different chunking parameters, different logics. Then you can really go directly into the Vega, actually search for the runs with the name Nosy Dog 582. then you have your disposal of your vector stores directly here. It's really great for the data lineage, the model validation people, they really like this solution, right? So in general, we are very satisfied with the Postgre, the PG vectors. It performs, it's cost effective, and it scales. We're currently running over thousands of virtual vector stores on a single instance of a Vega. It actually truly scales, especially come to experimentations. People can go crazy, right? In one go, they can create like 500 actually different experiment runs, and actually the whole thing just scales. One thing we are really happy with Postgre is actually they have a very AI-centric product roadmaps, right? Re-ranker logics, especially on the GraphRocs, we have a huge roadmaps actually in UBS, in using GraphRock in both supporting the investment decisions and also risk aversions. So I'm looking forward for the exciting collaboration with our team in Microsoft. Namely, let's go to then the basics. Is actually the PG vector just works. It's actually JSON-B document metadata is very flexible, allow the UBS to build very complex agentic retriever techniques. So now my team member Orhan is going to present some advanced features. Okay, Orhan, please.
Yep. Yes, actually what I would like to present will fall under the advanced React techniques in the slide that Maxim shown. So there is a part with agentic approaches. So what I would like to show is about that. Actually, it turns out that it is also very easy to implement in Postgres because it's a relational database. So instead of just having a streamlined process of just getting like 4 documents, doing the KNN, and then re-rank them, and then just introduce them to LLM context, we just let agent do it by itself. For that, we create tools. And these tools can be a full text search tool, a vector search tool, or a metadata search tool, which is like a JSON-B column in our schema, or a graph search really soon, or even a combination of them, as Maxim has shown. So we just encapsulate these as tools, and then we just let agent use it. And we name this AIR, so the abbreviation is Augmented Indexing Retrieval Search. Basically, I will just show an example of it. It is just going to leverage the JSON-B column inside a Postgres table to perform a tree search, which is quite similar to how we retrieve data in financial industry. So you get like 10 financial statements, and then you just try to look which one contains the relevant information, and then you just get the right section. Oh, okay, I need to get that. I need to look at the income statement, and then you just read that and try to perform a task. So this is exactly what the agent is going to perform. So I just uploaded like 3 years of Microsoft annual reports and asked some questions to it to demonstrate. So in this example, I just wanted the agent to compare between the gaming strategy of Microsoft between the years 2023 and 2022. So what it does first, it will list, in this collection, which documents do I have? Of course, we have the annual reports of Microsoft, so okay, but in this annual report, which sections do I have? Then it lists those sections, and then after loading the relevant sections, which is the gaming section, which is shown in the video, then it is just going to create this output. So compared to what you do in vector search, this is much more precise. Of course, if your corpus is like millions of documents, it's not going to work. But if you have a siloed corpora just dedicated to some use case, you can afford to do this kind of tree search, which is going to take some time. So let me give another example. So the advantage of the agentic approach, you can just throw in new tools to give your agent new capabilities. So I just also throw a Python interpreter to the mix, and then asked it to also come up with the calculation of cache ratio of Microsoft. So it lists the documents as usual and gets section names, and it loads a section about the financial statements in the annual report. It does it for the both financial statements, and then it creates a simple Python script to calculate the cache ratio, and then it just does the trick. And you can even add, more caveats to it. Like, for example, you can create an agent which can also create some document, send some email. So, for example, every day 8 a.m., please prepare me like a brief using the collection that we have in Vega. And the good thing with it is, basically in a Vega collection, you only get what you are authorized to. So automatically, everybody will have a different view of the data, and everybody will receive a different report on the same manner. So maybe we can pass to Q&A.
This is awesome. So let's switch back to our presentation. Oh, okay. So thank you for attending our session. So I think we have 4 minutes for questions. Before we start the Q&A, let me advertise a couple of other sessions that you'll have an opportunity to attend on this conference. So first, we have a lab where you will be able to play with the GraphRag and with the semantic ranker. So I certainly recommend that. So that is transform your apps with AI-driven features for PostgreSQL, Lab 4 to 6. So it's available today, on Wednesday, and on Thursday. Second, if you're interested in a broader spectrum of investments in Postgres, including very exciting topic of distributed databases, I certainly recommend you book these other sessions that we have on Thursday, which is called Driving Enterprise Performance with Azure Database for PostgreSQL. So that's breakout 191. So certainly mark it on your calendars. And of course, all of the blog posts and announcements that we made today are available here. You can take a picture of that. And last but not least, if you're interested in making some money during the conference, we have a PeerSpot sponsors somewhere around here, which you can contact to give us a survey, I believe, right? A review of the conference and kind of combine the good things during the conference. Okay, so let's start Q&A.
I have a question. Under the Microsoft campaign,
Sorry, can you use the mic, please? Thank you.
yeah, so the demo has a Microsoft 10K annual report. So when you guys load that, did you break that into sections or you load the entire?
Okay, maybe I skipped that part because of the time limit. So here is how it works. So we use GPT-4o image recognition in order to load the tables and also have the sections, because these 10K documents are, or like it's not the 10K document, but the annual report by Microsoft have also headings. And in our prompt, we also have some place. We just say, okay, be careful with the headings, and we just piggyback the last section. So if a section has multiple pages, we can also detect that like that. And basically, we leverage GPT-4o in order to get a textual representation of the document.
Okay, thank you.
Hi, thanks for the presentation. I'm wondering if you can give me just a little bit better intuition for the semantic ranking. My naive understanding would be if I'm trying to narrow down the vectors that I'm interested in, I don't just really want the most relevant ones, right? Because they might all be saying the same thing. I want diversity, like some kind of, I don't know, like principal components analysis or something of the vectors. why does just taking the most relevant ones the right thing to do?
That's a great question. I think taking a diverse set versus taking a relevant set is two different problems, right? So in order to really get a diverse set of documents that are still relevant, right, you actually need to use more advanced techniques than vector search. For example, GraphRag, when it performs kind of analysis of your data, it will actually find common topics, common communities, and that is an example of a more advanced technique that would produce kind of a more reliable, diversified set of results across like distinct topics. When we talk about the vector search in the example, right, the results that it was produced, it was actually off topic, right? It was relevant from the cosine similarity point of view, but it wasn't the type of document that I would consider like, hey, it's a diverse example, right? It was talking about some construction contracts instead of like relationship between landlord and the renter, right? So it was actually irrelevant data. So that's, I would say, if you want diversity, you need to employ more sophisticated techniques than just purely vector search.
Thanks.
Great. Any other questions? And we are at time, so thank you very much for attending this session.
Okay.